Welcome to the final in a series of 5 videos that have been developed in a collaboration between the University of Melbourne and the Victorian Department of Education and Training. These videos have been about maths learning difficulties and particularly dyscalculia. This final video is going to build on all the knowledge that we have acquired along this journey together and culminating now in intervention. So in this final video, we're going to draw on all the ideas we've used in the earlier presentations and provide some intervention advice for students with maths learning difficulties. More specifically, we're going to draw on our own clinical intervention framework to offer suggestions. In large measure, our framework was based on interactive assessment. This is a model of learning which aligns with the so-called Vygotskian approach to instruction and development. Now, Lev Vygotsky was a psychologist in the early part of the 20th century. Vygotsky believed that children were capable of much more advanced thinking and problem solving than when they're assisted by someone than when they're on their own. So that is to say, a more experienced other provides careful help and support for the learner. An interactive assessment is used both diagnostically, as an assessment, and also as an intervention measure. And I reiterate here, when I'm talking about diagnosis, I'm not talking about clinical diagnosis particularly. I'm talking about understanding the strengths and weaknesses of individuals so that we assess those and intervene appropriately. Now, the term interactive or dynamic assessment is used to distinguish from static assessment measures, which are our normal school-based or other area tests. What happens when you have a static assessment is you're assessing the performance of a student at a particular point. What you're not assessing is how they reach that point and anything about the learning along the way. And in particular, if the student got the problem wrong, what they didn't understand, where did they go wrong, what were the things that caused them not to be able to solve the problem. So it's often claimed then that the amount of help and the type of help that a student needs from interactive assessment is a useful way to identify different types of learning difficulties. And this is particularly useful in our present context because it's going to distinguish between different types of MLD. So what is dynamic or interactive assessment? Well, it's simple. It involves developing a mini learning progression within any kind of relatively narrow maths domain, like simple word problems. So just the steps that would be required for an experienced person to solve the problem are first determined, and then as the student progresses through the problem, then the experienced other person will provide guidance if necessary, provide scaffolding if the student gets stuck, and so on. So the steps required to solve the problem have to be first specified, and the focus is on the interaction because the teacher and the student collaborate to solve the problem. Now, the student might not have the competence initially to solve the problem on their own, but with the support for completing steps across problems from the teacher, saying things like, what do we do now? What did you know from the problem? What is the problem asking you to do? The responsibility to solve problems is handed over to the student. So the nature and the amount of help the student requires to solve problems independently, we would say, was the assessment side of this, and the ability to transfer across problems, which is a known difficulty for dyscalculics, provides an index of what is learned and a measure of learning potential. The long-term goal of interactive assessment, though, of course, is for the student to internalize the problem-solving concepts and procedures in order to solve problems independently. But an important point about interactive assessment is all students complete all problems because they are helped along the way. However many times they stop and need help, they finally solve the problem. And this addresses some of the psychological issues that students have with problem solving because they all succeed. So the principles then that are guiding our model of intervention and support are that performance variability and individual differences in developmental trajectories necessitate different intervention approaches. One size doesn't fit all when we're looking at intervention and support for learning, and we need to be able to accurately assess a student's core number abilities, and we've talked about assessment at length in video 4 now, their enumeration and their estimation, including number line estimation, which we talked about as a classroom-based activity. Their arithmetic abilities from counting to addition, subtraction, multiplication, division. Their fraction abilities, particularly assessing the errors they make, and their algebra abilities. And in algebra, we're interested in their understanding of algebraic reasoning. Now, as I said earlier, there are many competencies along the maths developmental pathway. I've focused on these. Core number and arithmetic for primary school are imperative for future math success, and then two well-known areas of difficulty, fractions and algebra, where these difficulties may be highlighted again. And again, diagnosis via assessment is critical to determine the appropriate intervention. So students with different kinds of difficulties then require different kinds of learning support, and the optimum intervention for an individual is based on their specific skills determined from assessments. And these outcomes will help also to identify the difference between deficit, delay, and expected maths learning pathways. And just referring back to the video clip in video 3 from the businessman who had a lifetime experience with dyscalculia, this isn't going to provide a cure, but we can have coping strategies. And the hope for these intervention strategies is that this is the building of some coping strategies for students with dyscalculia. So Fuchs and colleagues in 2008 articulated these 7 guiding principles for intervention, which are important for us to take into consideration as we work through these interventions. First of all, interventions must be instructionally explicit. Students need to know exactly what it is we're asking them to do. And then we need to minimize the learning challenge. Now, interactive assessment does this very well because it breaks it down into the smaller steps. But the student needs clear and precise, logically ordered explanations. Breaking it down into smaller parts always will help the student because it minimizes the amount that they have to learn, and also it will also isolate their difficulties. It's imperative too that we have a strong conceptual basis for any procedures. In previous videos I have talked about that if students apply a procedure, they can learn a procedure, but if they don't have a conceptual basis, they are going to forget that procedure. So this conceptual basis is important if you're introducing a procedure, making sure that you have presented the conceptual basis for it and reiterating that continually as the student uses procedures. The student will need to practice. Skill practice is essential, especially if the conceptual understanding is going to result from repetition of a procedure. We need to review where we're at now, where we've come from, and where we're going to go to. We're going to need some motivators to help students regulate attention and behavior, because often students, by the time we get into these intervention strategies, we find that they have been turned off maths altogether. Partly they're anxious about it, partly they just find it too difficult. So it's important that we motivate them and make it fun for them so that they do succeed. And that's an aspect of this success for everyone type of approach. We also need to monitor progress continuously. We need to know that the student is progressing, and if they aren't, we need to go back to see what it is that we need to intervene over. So, videos 1 and 2 then outline the development of children's maths ability from infancy to preschool to primary and secondary formal instruction. Difficulties for MLD children and students were described in each of the areas covered, and video 4 described many different measures of the ability, reflecting the different stages of maths development that we described in videos 1 and 2. In this video, we're going to consider intervention in 4 areas in turn: core number, counting and arithmetic, fractions, and algebra. Now, I'm going to not take a long time over this, but just to remind you of the sorts of difficulties that we've raised. I've talked about a short subitizing span. I've talked about difficulties with mapping on the number line. We've talked about counting difficulties, difficulties with multi-digit addition, difficulties with applying arithmetic knowledge in fractions and algebra. All of these are going to be addressed during this intervention so that we can see how students can be helped to overcome the difficulties. And before I go any further, I just want to dispose of this hoary old chestnut, and that is rote learning and conceptual learning. We're not going to distinguish between the two. I'm not going to talk about rote learning or conceptual learning for the following reasons. The support and the help that we give to students and their expectations is going to depend on their abilities. Sometimes an MLD student or one with dyscalculia will need to be shown explicit, well-described maths procedures several times before they begin to internalize that procedure. And they may need lots and lots of practice of that skill. So long as you are continually justifying why that procedure is being used in terms of the conceptual understanding, then eventually internalizing it will happen. And this process of internalization could be thought of the learner appropriating explicit learning behaviors for their own purpose. So they come to see the importance of understanding what they're doing as they perform particular procedures. And this in turn may be thought of as the first steps in constructing a conceptual framework. So rote learning may be the first step, particularly in dyscalculia, where we are needing to find other ways to teach. Dyscalculics have difficulty because of this mapping difficulty. That isn't going to go away. So we have to find other ways to teach them. And I'm going to also talk about an intervention strategy that actually specifically addresses this mapping to build that knowledge in dyscalculics. So there are many maths intervention support resources and sources of advice. A number of organizations provide paid supports to putatively help children learn maths. So there are online curricular software, board games, maths books and programs, specially designed maths component software, and the like. Indeed, between 1870s and 1970s, over 170 books with the title "Why Children Cannot Learn Maths" were published. How do we navigate this overwhelming array of support learning intervention options? Well, without the support of a significant other, students are often repeatedly asked to solve problems that they cannot solve. We find that students with dyscalculia will report that they have been asked to do many worksheets and they don't know how to start. And then this leads, of course, to failure, frustration, anxiety, and sometimes a fear of maths. So we need to link all that we've talked about in these videos, the assessment, diagnosis and intervention, so that we can get the best outcomes for all of these students. Now, we live in a digital universe, and students, as you know, are far more digitally aware than those of us that are older. And this online support is useful for identifying the range of mathematical phenomena. And we need to encourage students to use these as it's a familiar medium. They're used to working online. And online programs often include dynamic displays, and students actively interact with the program so that the program is building on the student's knowledge. But is this enough? The importance of learning maths depends on extracting principles and linking dynamic concrete representations with abstract maths ideas, and that may not be if the student is going to just work on the online program on their own and unassisted. However, if we have external support from a more experienced person to ensure that this understanding is being realized and that the student is understanding what they're doing as they're working through these dynamic arrays, the outcomes may well be different. And that support person is going to focus on generalizing across problems and transferring to new problems. Two important steps that need to be made when students are learning how to work with certain problems. They need to be able to generalize it to other problems and transfer to new problems. Students also need to be self-motivated and have increasingly less support. But that isn't going to happen until they are able to understand what is being presented to them and how they are to interact with it. And the other thing to not lose sight of is that maths is implicitly embedded in everyday activity. One very useful intervention strategy is you're driving along the road, the speed limit changes, and you say to your dyscalculic son or daughter, am I to go more slowly or faster? Simple things like that in every day, students will, it's a little bit like hiding vegetables in hamburgers or beef burgers. Students won't realize that they're actually processing with numbers if you're introducing them into their everyday life. So let's now look at intervention in the core number area. Students enter school with a considerable amount of number knowledge. The home learning environment in early years can promote or inhibit the development of arithmetic competence, though, and that may be why we have such a variety in preschool students when they're entering school. The frequency of number activities in the home has been associated with math skills at the start of school and then into grades 4 and 8, and this is part of this Trends in International Maths and Science Study data from 2012. So there is an important contribution that the home is making to the outcomes in schools. Numerical activities have specific effects over and above parent education and socioeconomic status, according to the same study. And children who start school with poor knowledge and skills in numeracy are unlikely to catch up to their peers. Now that's a quote from this paper, along with individual differences in numeracy skills are evident at school entry prior to formal instruction, suggesting that children acquire fundamental skills at home. Now, what this is saying is that the evidence is that students who are entering the school are going to be somewhat disadvantaged. And the whole purpose of this intervention video is about that. If a student, when they enter school, is already having difficulty in numeracy, then early intervention is the answer. But equally, should we be assisting parents in optimizing children's number skills as early as possible? If there is some disadvantage from what they learn prior to school, perhaps we need to do some work in making sure that all children are entering school with a certain basic toolkit. So before we start to detail specific intervention strategies, let's just try this. So I'd like you to please solve the following arithmetic problems. Here's the first one. There's the second one. And there's the third one. Now I won't make you go on with that because I suspect that for many of you, you didn't know where to start with it. So what might have helped? Well, if you'd known that that was the symbol for 5 and that's the symbol for 11, you would have been able to do that sum easily. And you would have got the answer 16, but you then need to know what the symbol is for that. If you'd known that this is 24 and that's 17, then you would know that that is going to be 7. That's subtraction, and you would again need to know the symbol. And if you knew that that was 2, and that's 9, you'd be able to know that that was 11, and you'd insert the symbol that you can see there for 11. Better still, though, if you knew that those symbols represent those arrays, and you could relate it, then that would make life much easier. So what you've just experienced is what it is like for a student with dyscalculia in a maths classroom. That is how they feel when symbols are presented on the board and they're asked to do things with them, but they don't know what the symbol represents. So we've described dyscalculia as this deficit in the most basic capacity for number, this number sense, and on which everything is built in maths. For dyscalculics, the relation between number and symbols, words and arrays is not secure. Without number sense, a dyscalculic struggles with the principle of commutativity. That is 3 plus 7 equals 7 plus 3. Or with the relationship between addition and subtraction. If 5 plus 3 is 8, then 8 minus 5 is 3, and 8 minus 3 is 5. We've already emphasized the importance of an accurate assessment of student-specific maths ability. Students are different, and the support they need will also be different. Prior to any intervention, assessments designed to identify MLD students in terms of delay or deficit are paramount. And an understanding of number concepts, number structures, and calculation procedures helps support dyscalculics in the difficult process of trying to learn and remember them. So this means then that any intervention for maths difficulties, from core number understanding right through to the higher maths abilities, has to begin with activities designed to strengthen number sense for all students. Going back to the basics is going to be an important part of making progress later. So one known difficulty then is this abstract nature of number. And we talked earlier about the arithmetic difficulties experienced by students once problems cease to include pictures and move to that. So what helps cement this relationship between number symbols, words, and non-symbolic array? In the early stages, guide pupils using concrete materials, for example, and then use them to split and combine sets of objects. Students move on to solve problems without manipulatives, but it's important not to move on until you're secure in knowing that they understand what they're doing with the manipulatives, but keep them still available to check the answer or assist when stuck. And then, of course, digital activities can also be used, but again, they need to be adaptive. They need to use the learner's previous performance to determine the next task. So several interventions have been developed that target these early numeracy skills, including something called number sense interventions by Jordan and Tyson. These are evidence-based interventions supporting the development of key math skills such as oral counting, number recognition, numeral writing. And there are 24 scripted lessons, and they're about half an hour each. And the specific skills that are being developed here are recognizing quantities and numerals, making associations between numerals and quantities, writing numerals, solving story problems, and solving written equations. But these are the sorts of tasks that are going on in school all the time, and so you don't necessarily need to go and get a specific version of this. It's available by just looking through the worksheets that you work through, and it might include something like this, where you have 4 objects and you have to select whether it's 4, 2, or 3, or the student has to select. All of these sorts of things are quite easily replicable in schools. Board games such as Snakes and Ladders are incredibly useful. In the video clips of video 2 on dyscalculia, you might have noticed there was a Snakes and Ladders board on the table there. They are used often in intervention for dyscalculia. And the reason is twofold. One is the dice that they have to shake to move have non-symbolic arrays, but the game depends on counting the relevant number of squares expressed on the dice, which means that the student needs to be able to relate the non-symbolic array to the numeral and then count appropriately. And then the other thing about a snakes and ladders board, it's a little bit like a number line. It's presented in a sort of number line fashion, and it shows the relative positions of numbers along that line in an equal spacing. So magnitude representation, spatial ability, number line abilities are all being reinforced through snakes and ladders. Specially designed online programs to increase understanding of the mental number line have also been developed, and it might look like this. The grasshopper jumped forward 7 and backward 6. Choose the matching example. Again, this can be replicated easily in a classroom. And the aim of digital interventions, as with teacher interventions, is to make numbers meaningful for the learner. And recently, Professor Butterworth and his wife, Diane Laurillard, developed this game called Number Beads. And it uses this level progression approach to try and build this mapping between the non-symbolic form of a number and the symbolic form. And if a child is thought to have dyscalculia, that is, they have this poor number sense, it's likely that they will need help in this decomposition and composition of sets or groups, and also with approximation. So the idea here is to use a method of vanishing cues. So it's a little bit like our interactive assessment, but instead of having an adult supporting, these are cues that are presented to everyone at the start, and they diminish as time goes on. So the first presentation then is a colored sets of beads, no digits to be seen. And in fact, the color strings are, each color represents a single numeracy. So the target for here is 4, and the idea is that the student has to make groups of 4 out of what they're presented with. So they might divide that into 4, and it will separate and make 2 sets of purple 4. Or they might cut 1 off that array, and you will then get a 1 white and a 4 purple. Now, they find that they have a 1 and a 3 that they can combine, and that will make another 4. And as they run out of beads, more beads come onto the screen for them to successfully make up to 10 of these combinations. Now, the next set of screens, once they've completed those ones, the target is still there and it's still colored, but it now has a numeral with it, so that the student will start to associate the numeral with the target. And the task is exactly the same. You've got a target of 6, so you can cut 2 off the 8 or 1 off the 7 and so on, and then you can combine ones that you've got left over into 6s. Then it goes into white beads in case as that cue of color goes away, so that the student is not now looking at the color, they're looking at in fact their attention is now much more drawn to the symbol than the array, because the color has gone away. There is a stage 4 where there are digits, but when they split, they do become the beads. But the last one is simply digits. So through these 5 stages, and there are quite a few repeats within the stages, quite a few levels, the student has moved from a totally non-symbolic version of the number into a totally non-symbolic into totally symbolic, with some cues that help them to make this transition. And there is clearly success. The measurements that are coming out of this would suggest that dyscalculic students are forming associations that it won't be their intraparietal sulcus necessarily, but the brain is forming new associations to join the non-symbolic form with the symbolic form, which is this important mapping that all students need to make progress. Dyscalculics are able to make better sense of number when the teachers use concrete materials such as beads, counters and toys. Composing and decomposing sets of blocks accompanied by counting helps dyscalculic learners understand the foundational concept that numbers are made out of other numbers, and using concrete objects provides a presentation of the relationship between addition and subtraction and between multiplication and division. For example, if we take 30 counters and share them between 5 children, and then we take the same counters and share them between 6 children, what does the student notice? Now, they might not notice anything the first time you do this, but if you do it often enough, they may come to notice that 5 lots of 6 and 6 lots of 5 come to 30. So the aim is to draw the student's attention to these patterns of relationships between multiplication and division and how a single number fact can be used to develop other number facts. So, for example, students with MLD may need many examples of this sort before they'll notice and internalise that 5 lots of 6 are 30 and 6 lots of 5 are 30. And then they might find in the division domain that if you take 30 objects and you divide them between 5 people, each will have 6, and you divide them between 6 people, each will have 5. They will need many repetitions of this, but one would hope that eventually they will start to instantiate some of this knowledge. Similar activities can be used for addition and subtraction, but the important point to raise here is that dyscalculics often seem to understand a concept one day and forget it the next, and the likely reason is that they're learning procedures without connecting to any kind of conceptual basis. And it's the conceptual basis, and that's this issue of checking that they understand. And they fail to remember the list when they're presented the next time if they haven't got a conceptual understanding. So this is why we need to continually check that they have this understanding. And this brings us back to dynamic assessment. With a more experienced person, the intervention doesn't rely on the student making assumptions about relationships. They are being pointed out to them. And often we rely on a student to make connection between the process and the deeper level of understanding, where in fact that's not a step they're able to take unassisted. So this support person can encourage the student to talk through their thinking processes. Think back to Trish. She talked about the importance of talking through as you're working through, and then you get this idea of how they're understanding the learning process. So it provides detail about their specific learning difficulty, and it also supports them in mastery of the task, which is most important. Now let's consider this word problem. Josh's mum buys him 5 pairs of socks. 1 pair costs $2.85, but a 5-pair pack costs $6.50. How much does she save by buying the pack? Now, interactive assessment is particularly valuable in this kind of problem because the problem can be broken down into the steps that are needed in order to solve it. And the student might not know where to start, so the support person would ask questions like, what is the question asking you to do? What do you already know? And successful word problem solving involves these several processing steps, and the difficulties experienced provide information about how the student has understood the problem. Now, students might need help to overcome a number of difficulties along the way within a single problem, and this is what will be provided through these specific prompts by the support person. Now, I will be talking about interactive assessment in more detail, the specific prompts, towards the end of the video when we talk about algebra word problems. Multi-digit subtraction intervention, again, this was an error that we pointed out. And note again, I'm going to talk about concrete materials. The use of concrete materials is really, really important for students with math learning difficulties. So here's the problem, 300 minus 139. The first thing the student needs to do is to get out 3 100 blocks and display it. And then they'll write the problem in a column-aligned format. Now they notice immediately that they can't take 9 and they can't take 30. So the first thing they need to do is to trade one of their blocks for 10 blocks, 10 blocks. And they need to then note that in their question here, they've taken one of the 3s, that becomes a 2, and they've put 10 in the 10 So they've got 200 blocks and they've got 10 10s. The student then needs to trade one 10 block because they still can't take away that 9. So they now trade one 10 block for 10 unit blocks, and they again note the trade on the question. So now they're in a position to be able to do all the subtractions. They can take 9 from 10, they can take 3 from 9, and 1 from 2. And that's precisely what they do. And they then can see what is left, which they would then write in the solution. So using these blocks to do that kind of subtraction addresses this error of not remember. If you just do it by rote and you cross out a number and you move things along, you're not going to necessarily do this error-free. If you use the blocks, you are very likely to get the question right and also to have a visual picture of what's happening. So in summary then, intervention is based on understanding basic number concepts, core building blocks. The sequence of activities is carefully structured to adapt to the learner's current level of understanding. Instructions are explicit with a strong conceptual basis. The learning challenges should be minimized, so in clear, precise, logically ordered, small steps. Frequently checking that the student understands and revisiting the same concepts is imperative. The intervention should make arithmetic learning a positive experience. If they can achieve an answer for every question, they are going to feel more positive about it. Learning should be fun, motivators to help students regulate their attention and behavior. And now we move to fractions, which we talked about as one of the areas beyond primary, although they are introduced in primary schools, where problems occur. So they're important in and beyond school, and many students don't understand them. What's the best intervention? Well, as with all other interventions I've discussed, using concrete materials so that they can connect the physical forms of fractions to the written fractions is as important as connecting symbolic numbers to non-symbolic arrays. It's the same kind of thing. But you need to be aware that if you only use circles or you only use fraction bars, students won't be generalizing their learning. So you need to do it in a variety of concepts. When students count fractional parts, they need to do this using manipulatives on number lines or orally, and this will help them understand fractions are actually numbers. So explaining the meaning of fractions to students using clear language, for example, explaining that 3/4 means 3 of 1/4 units, which means you've got one whole, you've divided it into 4, each one is a quarter, and you take 3 of those quarters. Or it could mean 1/4 of 3 wholes. And a useful explanation for understanding fractions is this relationship between the division sign and a fraction. And that is that a division sign is a fraction with no numbers added. And if you think of it that way, then you are going to get this rational number approach to fractions, that 2/3 means 2 divided by 3, because it's like a division sign, only you've put some numbers into it now. So you can distinguish where we've got 1/3 of each of 2 wholes or 2/3 of a single whole. And those two things mean exactly the same thing. Those two diagrams mean exactly the same thing. And it helps for students to understand the way in which fractions are actually constructed from the numbers. It also helps a greater understanding of what happens if we count in fractions. And so, for example, you can count and get the same numerator and denominator to get improper fractions when you've gone beyond the whole. So, for example, we could start with 2/5 and count up one more fifth, and then we got 3/5. Now, this is something that's often missing in students' understanding, that they don't understand that 2/5 and one more fifth is 3/5. And then they can count on 4/5, 5/5, which is one whole, and then 6/5, which is beyond the whole, so that students are going beyond the single unit, which is often used in fractions, and they understand the pattern. And this will form the foundation for adding and subtracting fraction. An inherent source of difficulty is understanding fraction magnitudes, and understanding them can make a huge difference. So encouraging students, and remember back to an earlier video where we talked about this difficulty of 1/3 plus a half equal 2/5. Why can't that be correct, you say to a student? And then by getting them to cut up objects into thirds and halves and sticking them together, they can see that it's much more than a half already. But so 2/5 can't be right, because that isn't even a half. And then you might encourage them with some plausible answers. You might say, well, supposing we were to take and cut up this circle into sixths, and then we've got a third, which will be 2 sixths, and a half, which is 3 sixths, that's 5 sixths. That's nearly the whole, so it can't be 2 fifths. Lastly, we're going to just look at some algebra intervention. And in video 2, we describe the types of difficulties students make when they're making this transition from arithmetic to algebra. And we highlighted 4 areas. The use of variables, replacing numbers, where arithmetic has a specific numerical answer, algebra has a range of answers. Difficulties with the equal sign, arithmetic interpretation as a unidirectional left to right operator, replacing gives or yields or results in. Solving algebraic equations, that arithmetic processes based on this unidirectional left to right interpretation are inappropriate for equations when you've got unknowns both sides of the equal sign. And solving algebraic word problems. These are more complex than arithmetic word problems because they involve constructing an equation to represent the mathematical relationships first. Now, many students have difficulty with the transition from arithmetic to algebra, but the problems are magnified for students with MLD who don't have a well-grounded understanding of number in arithmetic. So algebra often involves manipulating expressions based on a sound knowledge of the structure of the expression built through arithmetic experience. So just to reiterate, students with maths learning difficulty and dyscalculia may need to step further back before embarking on these algebraic interventions. So after many years of experience with arithmetic problem solving, students often interpret the equal sign in this unidirectional left to right way. And early algebra is very similar to arithmetic, and arithmetical procedures can be correctly applied in early algebra, and that really is what leads to these difficulties. For example, this equation, p plus 6 equals 11, is basically an arithmetic equation of the sort primary students have seen many times with a box in place of the letter. Problems like this reinforce the arithmetic one-directional interpretation of the equal sign, which later presents problems for algebraic problem solving. However, the same problem could be presented like this. 11 equals p plus 6. It's exactly the same problem, but presented differently. And this would assist students with the transition to a bidirectional interpretation of the equal sign for algebra. Now, students, when they first see these, will express concerns. They will say, it's back to front, I can't do it. But this is an opportunity for teachers to explain the meaning of the equal sign. And better still, when arithmetic is being taught, also presenting the equations that you present with boxes in arithmetic, presenting those in the other way around will also challenge this idea of a one-directional operator for the equal sign. And it will make a large difference to students as they're approaching algebra. So interactive assessment is particularly valuable in algebra, particularly in word problem solving, and where there may be many areas that the student has difficulty with, and we need to know what those all are. So diagnosing these specific areas of difficulty when you've got 4 possible ways a student can go wrong in algebra is very important. There's not going to be time in this video to address interventions in all 4 areas, but I'm going to talk about algebraic word problem solving because this actually encompasses the other areas that present difficulty. And it involves 3 problem solving processes really. Comprehension, where you understand what the mathematical relationships are in the problem, what is the text of the story problem telling you. A representation phase, where you represent the information that you're given in some form of symbolic language, usually an equation. And then a solution phase, where the equation constructed in the representation phase is solved to generate a numerical solution. So let's consider this problem. Julie's 16-year-old brother is 8 years older than her. How old is Julie? So we need to convert this into a symbolic form, And what we're going to do is we can't just look at it and do a word order, make an equation out of it. And this is a particular challenge for MLD students because they need to understand the maths, underlying maths relationships. To construct the equation, the unknown part of the problem is first expressed as a variable. Then the remaining relationships are built. So if Julie is 8 years old, is X years old, how old is her brother? He is X plus 8 because he's 8 years older than her. We know, though, that Julie's brother is 16 years old, so X plus 8 equals 16. And solving this simple arithmetic equation gives Julie's age as 8. So some students might find all these steps difficult to negotiate, and interactive assessment provides a series of hints to assist in negotiating each stage. And then the specific areas of difficulty are revealed from the hints required. And importantly, all students reach a solution, and this reduces their anxiety when they approach a new problem. So these are the sorts of hints then for conceptualizing the problem. Read the question carefully. What are the important facts being given? In representing the problem, and again, the student may be able to work through a number of these steps with no help at all, and then they get to the point where they've made the unknown value, but they don't know what to do next. And so you might say, well, let's build an equation starting with the pronumeral or the letter that you've already generated. Sometimes students get blocked once when they're trying to make this expression if the problem is quite complicated. And you may need to give an analogy. This is still a representational skill, but the analogy is relating it to perhaps themselves and their siblings. And this analogy hint will help contextualize the problem and help them make this step. So to summarize, the research-based instructional principles that we've covered in this video are to enhance number sense, and that can be done through intensive number comparison or linking number to space through the number beads, for example, or it could be using the number line estimation task to instantiate the spatial array of numbers. We need to cement this non-symbolic symbolic link. Repeated association of non-symbolic and symbolic numbers will assist with that. Increasing reliance on symbols and removal of the manipulatives, but making them available if needed still. We need to conceptualize and automatize arithmetic. Students can't just apply procedures without having a conceptual understanding. So we start with concrete representations and then we move to learned number facts from those. And of course, we need to maximize motivation through positive reinforcement, reducing difficulty by adapting to the student's needs and consistently referring to numbers in the environment. And last but not least, let's make it entertaining for them. Let's make it into a game. That will help them understand. Now, there are some workbooks there for you to access. There are many websites for understanding learning difficulties. I hope that some of what's been presented, though, will give you at least some stepping stones to the remediation for students with maths learning difficulties. Now that concludes this series of videos about maths learning difficulties and dyscalculia that were developed in this collaboration between the Victorian Department of Education and Training and the University of Melbourne. If there are any references that I've made that you'd like to follow up, or any further information you'd like based on our clinical experience of working with MLD students and dyscalculics, please don't hesitate to contact the department directly or ourselves. We are easily accessible through the University Find an Expert link, and our email addresses are there. And I'd like to thank you for your attention to the material I've presented today in these 5 videos over time. We hope you found them informative and useful.